Hi everyone, can you hear me? So, good evening everyone. How are you all? Okay, so I hope you are doing great, right? So, today we are going to start a very new topic, which is discrete and continuous random variable. So, more specifically, we will be starting discrete random variable in this particular session. Okay, so let's get started. Now, as I just said, the topic name is discrete random variable. Cool. Before I start, do you remember that what is discrete random variable and what is continuous random variable? Okay, recording is on, right? Okay. So, do you recall that what is discrete and what is continuous random variable? So, let me just probably make you recall that what was the discrete random variable and what was the continuous random variable. Or maybe let's just do one thing. We will recall it after the discrete random variable. I mean, before I start the continuous random variable, then at that time I will recall you. So let's just see the gate syllabus before that. So as you can see here in the gate syllabus, we have few of the topics in the probability, which is the random variable, and the conditional probability, which we have already covered, right? Conditional probability, random variable, standard deviation, and these kind of things we have already covered. Now, if you look at the syllabus, then there are some other topics which are looking like uniform random variable, right? Uniform random variable, exponential, normal, Poisson, binomial distribution, and these kind of things. So just see here that this random variables topic has been covered. I hope you have understood that what is a random variable, right? So can you just tell me what is a random variable? Random variable is something which maps a outcome to anyone real value, right? So that's what random variable is, right? So it is a function basically. Now this topic is covered. Conditional probability has been covered with the tree method, and a conditional probability and Bayes theorem, these things has been covered with the tree method. Now if you look at this, then this is the portion which is basically called the statics. Okay, so I mean, if you see that probability and static is a topic name, and then probability is a major area, which means 95 or maybe 96% of the area is probability. Recently only, just at 1-2 years back, they have added this mean, mode, median. Okay, these terms here, specifically this mode and median. Okay, mean is just expectation, and standard deviation is just square root of variance that we know. So specifically, they have added two terms, which is median and mode. Actually, I don't remember that if they have asked any question from median and mode till now from the gate PYQ. It means like probably they have not asked anything. But we will see this like how to find the median, what is the median and mode later. Okay, but now what I'm going to cover is basically discrete random variable, and inside the discrete random variable, whatever you can see as an underline, which means the uniform random variable, the Poisson random variable, and binomial distribution. These are specifically in the syllabus of discrete random variable. Okay, so let's just see that what are the famous examples of discrete random variable. So now till now, what you know is that what is a random variable, right? That's all you know. I'm not assuming that you know anything else. So I just assume that you know what is a random variable. And now let's just see what are the discrete random variables. So what I'm saying here is that some of the famous examples of discrete random variable. So what do I mean by the famous example? Let's just see. See, there are these four are famous examples of discrete random variable, which means that let's suppose I have a random variable x. Okay, I have a random variable x which takes value 1. I can define my random variable to be anything which takes, let's suppose, value 1, or maybe only 1 and 0 it only takes. Okay, let's suppose that for some outcomes, okay, for some outcomes it takes value 1. Okay, and for some other outcomes it takes value 0. Some other outcomes, suppose that is the case. Now, in this case, you will say that x is some discrete random variable, right? Why? Because it is taking only the finite values in this case. So you will say x is a discrete random variable. I hope that's fine. Now let's assume that with some probability, okay, I mean with some probability, maybe you can say with some probability p, it is taking 1, and with some other probability 0, it is taking sorry, with some other probability which is 1 minus p, it is taking 0. So suppose with probability p, generally we write with this short form with probability p. Have I used this short form before that? I don't think, right? Okay. Actually, this is very, very popular. Actually, there is nothing in this short form, but yeah, this is very popular short form. This is W dot P. It means with probability. Okay. In many of the textbook, you might see this short form with probability. Okay. We thought it means WhatsApp. No, this is WP, right? How can it be WhatsApp? Okay, so let's just continue. Now with probability, let's suppose 1 minus p, it is taking 0. So x is a discrete random variable. Now it so happens that this kind of phenomena where x takes the value 1 or 0 is so often, I mean, see, this is a discrete random variable, this is one thing. But another thing is that this is so often so used to used to phenomena in the general nature that we have a specific name for this discrete random variable. And what is that specific name? Can anyone tell me? This is called Bernoulli random variable. Yes, indicator random variable or Bernoulli random variable is more popular. This is called Bernoulli random variable. Basically, x is a discrete random variable. That should be clear to everyone first. Okay, this is the first step to understand that whether x is a discrete random variable or not. Are you all convinced that x is a discrete random variable? Let me know. Are you all convinced that if x is taking two values, 1 and 0, then it is a discrete random variable, right? Now, the next step to understand that is there any specific type assigned to this x? Okay, so it so happens that 1 and 0, this kind of random variable are so famous, so popular that people have given them. I mean, the scientist, obviously the Bernoulli, they have, this scientist has given the name to this random variable, and he said like, okay, let me define my own random variable, which is x. Okay, so this particular random variable is very, very famous. Right? So that's why I'm calling it Bernoulli random variable with some name, which is Bernoulli random variable. Let's define a random variable x. Let's define a new random variable x, which is taking three values. 1, maybe let's suppose which is taking three values, 0, 1, and 2. And with probability, anything. I mean, you can have any probabilities. Let's suppose with probability p, right? With probability p1, with probability p2, with probability p3. Let's suppose x is a random variable which has these 0, 1, 2. Only the possible values of x is 0, 1, 2, which means that p1 plus p2 plus p3 is actually 1. This is a valid PMF, let's suppose. Right? Bernoulli random variable takes two values. Yes, Bernoulli random variable takes only two values, which are 0, 1. I will talk about Bernoulli random variable in a minute, but let's have some intuition that what do I mean by the famous random variable. Let's suppose there is a random variable x which takes three values, 0, 1, 2, with the probabilities p1, p2, p3. Such that p1 plus p2 plus p3 is 1, which means the only possible values that x can take is 0, 1, 2. Can anyone tell me that what is this random variable? Anyone? Twinkle is saying Bernoulli. Okay, no, there is no such name. Okay, first of all, tell me, is this a discrete random variable? Right, this is a discrete random variable. Okay, great. Now, this is a discrete random variable, and let me tell you the name of this random variable. This random variable name is goclasses random variable. Okay, I just defined my own random variable. Okay, which means that I can define my own random variable, but but unfortunately, that I cannot make it popular. That's the only problem with this random variable. I mean, I want to make it popular that everyone call it goclasses random variable, but I can't do it. Reason being is that it might not be occurring so often. Right? So basically this random variable I just defined, and you can define your own random variable and you can name it, but it might not be so popular. That's why people might not be using it. That's the only problem with this random variable. So you can define any random variable, but there are certain random variables which has a certain PMF. PMF means probability mass function. So there is a certain PMF that occurs too often, which is basically x equal to 1 and x equal to 0 with probability p and 1 minus p. This is some PMF which occurs too often that we say that it is a specific one famous random variable, which is a Bernoulli random variable. Similarly, there is another PMF that occurs too often, and then we say this is a binomial random variable. There is another PMF that occurs again too often. Then we say this is a position random variable. Similarly, there is a PMF that occurs too often that we say this is a uniform random variable. So basically, this is just a famous random variable. There is nothing special about it. Are you getting my point? Which means you have certain PMF. You have assigned that PMF a name. Okay, so why I'm calling, see, this is not my term. The famous is not my term. I have taken this famous word from one university. I mean, this particular slide is from one university. I actually, sorry, I forgot to write that university name. But yeah, I can just tell you later. Might not be MIT. Maybe I could have remember if it is what MIT, or maybe it is MIT. I don't remember exactly. Okay, it doesn't matter anyway. So basically what I'm saying, this slide is taken from one university, and then they are calling them famous random variable, which means they don't have any specific semantic. It is just that some PMF was very popular, and then we call it famous random variable. That's it, right? Okay, so I hope you understood. Cool. Now let's just see one of the popular PMF, which is a Bernoulli random variable. Okay, let's just see one of the popular PMF, which is Bernoulli random variable. Now, let's see what is written here. So they are saying that for all its simplicity, the Bernoulli random variable is very important. Okay, I mean, it is so simple random variable that it by itself becomes very important. And as I just gave you the hint that what is a random variable, this Bernoulli random variable, it takes only two values. The x takes only two values, either 1 or 0. It takes 1 with the probability. I mean, you can assign any probability, but if the experiment with the probability p, with probability p, and with probability 1 minus p. Otherwise means with probability 1 minus p. So basically, what happens? Let's suppose that you have some sample space, right? Let me denote this sample space by omega, capital omega, right? Now, let's suppose that there are certain outcomes in this sample space. Okay, there could be many outcomes in this sample space. Let's just say there are certain outcomes in this sample space. Now, what is happening? That I am saying that there is a random variable x which maps every outcome to. Can anyone tell me? Either 2, it can map to either 1 or 0. Yes, either 1 or 0. Let's suppose that half of the, or maybe it doesn't matter half or not. I mean, let's suppose some of the outcomes it is mapping to 1. Okay, some of the outcomes it is mapping to 1. Another set of outcomes it is mapping to 0. Right? Let's suppose that another set of outcomes it is mapping to 0. And this is x. Then x is called Bernoulli random variable. Okay, x is called Bernoulli random variable. So what is happening here? You have a sample space, and some of the outcomes are mapped to 1, some of the outcomes are mapped to 0. Then we call, if x is doing so, then we call x is a Bernoulli random variable. Let me give you some concrete examples. Suppose you toss क्या बोलते हैं उसको, coin. You toss a coin, right? Tossing a coin. Let's suppose you toss a coin, and then suppose that I say that x is taking, let's suppose that, okay, x is mapping head to maybe 1. Let's just say that, okay, x is mapping head to 1 and x is mapping tail to 0, which means that in my sample space either head can come or tail can come, right? And x is something which is called Bernoulli random variable, which maps this head, I mean, some of the outcomes to 1 and another outcomes to 0. Then x is called Bernoulli random variable here. If I just ask you what is the probability of x being 1, then you will say this is same as probability of head, right? This is same as probability of head. Is this okay to everyone? I mean, this is just one example. Let me give you more examples. Maybe you will get to understand more. 0 1 की जगह 1 2 नहीं हो सकता क्या? No, I mean, no, that is not the definition of x. Right? That is not the definition of x. This is specifically 0 and 1. Okay. Cool. Now, let's just see another example. Let me just say this is another example of Bernoulli random variable. Let's suppose you are rolling a die. Dice or die, whatever you want to call. Okay. Doesn't matter. Let's suppose you are rolling a die, and then you say that the possible outcomes are 1 2 3 4 5 6. Now suppose some of the outcomes are getting mapped to 1 and another set of outcomes are getting mapped to 0, which means I can say some of the outcomes maybe you can consider that, okay, 1 to 5, 1 to 5, yeah, even odd is also good example. Let's just suppose 1 to 5 are mapping to 1 or 0, something like that, right? It is mapping to 1 and it is mapping to 0. Okay, just for the sake of example, Twinkle is giving even odd as an example. Yeah, that is also a good example. So I can say that I can say that, okay, X is mapping. Let's suppose this is the sample space that I have, where I have 1, 2, 3, 4, 5, and 6. So I will say that all of these, right? All of these in my sample space are getting mapped to 1 based on this X. You can have any X, it doesn't matter. I'm just giving you one example. And then this 6 is getting mapped to 0. So here X is Bernoulli random variable, right? This is X which is doing so. It is Bernoulli random variable. Is this okay to everyone? I mean, at least the definition is okay to everyone, that what is a Bernoulli random variable? It is basically mapping some of the outcomes to 1, another set of the outcomes to 0. That's all the Bernoulli random variable is doing. Okay. So basically, we say, I mean, it is up to you how you define your success. Okay, success. I mean, everyone has their own definition of success. So does the Bernoulli random variable. So here, what I'm saying, that you can define your own success. Let's suppose I say that in tossing a coin, if let's suppose I say that getting head is success, maybe you can say getting tail is a success. Okay, I mean, it is up to you. Getting head is a success. Let's suppose you say getting head is success. So in general, we say that probability of success, okay, probability of success is basically P, which means that if I have some experiment, I mean, probability of success is basically the probability of head, right? I mean, getting head is a success, then probability of head and probability of success are equal. So if I say that if I have an experiment where I can classify my outcomes as just a success or failure, then I will be making use of what? Bernoulli random variable. Okay, let me write down this line. So if we have some experiment, where we can classify, okay, every outcome as success or failure, then we say we can have Bernoulli random variable, right? Okay. Now here in this case, I'm saying the probability of in this case, I'm saying getting head is a success, right? You can also say that getting tail is a success. Okay. So in this case, I'm saying generally success means that get like 1. Okay. I mean, whatever outcomes this X is mapping to 1, that is called success. So basically, I will here, can you just tell me what is a success? Can you just tell me in terms of English language, what is a success in this experiment? Yeah. Less than 6 or maybe less than equal to 5 is success, or greater than 5 or maybe equal to 6 is failure, right? So basically, if I can divide my sample space in just 2 parts, where half of the, sorry, not half, I mean, some of the outcomes are leading to success, some of the outcomes are leading to failure, then we say we can make use of Bernoulli random variable, right? I hope that is fine to everyone. Cool. Okay. Should we continue, or there is any doubt here? Maybe we can see one question, and then we will come back to if you have any doubt. So let's just see this question. What they're saying: consider a random variable X which takes a value 1 or 0. Now they're saying X equal to 1 or 0 if we have head, or 0 if we have tail, right? Now probability of X being 1 is P, probability of X being 0 is 1 minus P. Now they're saying what is the expectation and variance of X. First tell me, for this question to solve, do you actually have to know that this question is related to one only random variable or some specific random variable? No, right? They have given you PMF and then they've asked you to solve the question. Actually, that is true for all the questions, for any type of random variable. Okay. I mean, if you know that what is the PMF, you can solve that question without even knowing that what is the name of that. It is just that some of the PMFs are so popular that they don't give you PMF sometimes. They will just say the name. And that's why we need to know the name. That's the only problem. which means that they might not give you the PMF sometimes. Okay, sometimes they will just give you the name. Maybe they will just say that it is a uniform random variable. Okay, maybe they will just say it is a uniform random variable. At that time, they might not give you PMF. Maybe they can just say it is a position random variable. At that time, they might not give you PMF. Similarly, they can say that it's a binomial random variable. At that time, they might not give you PMF. That is the only thing. That's why we have to know that given a name, how how to understand that name. That's why we are studying this topic. Understood what I'm saying? So why the names are important? Because for every name, correspondingly, there is a PMF, or vice versa. For every, for these four popular PMF, there is a name. So basically, this is a one-to-one corresponding kind of thing. This is a definition basically. For Bernoulli random variable, the PMF is fixed, which is this. Similarly, I will tell you the PMF for these random variables, right? So sometimes what they will do, they will just say the name. They will not say PMF. That's the only problem. That's why we have to study this topic. Otherwise, we don't have to study this topic separately. Okay. So here, in this particular problem, although if they could have want, then they could have just said that, okay, X is a Bernoulli random variable, right? X is a Bernoulli random variable instead of giving you the PMF. But yeah, if they are giving the PMF, that is okay. Cool. So now they're asking you to find out the expectation and variance. So I think you can do it, right? Expectation is coming out to be I think 1 into P plus 0 into 1 minus P, right? So this is P. And what is the variance? Okay. First find out the expectation of X square. Let me know if everyone is comfortable with the finding out the expectation of X square. Because we have this as a separate topic also. Do you remember what is this rule called? Yes, this rule, actually, we don't need to remember it. That's why I don't care if you remember it or not. But yeah, this rule is called lotus. So I was saying that we need to find out the variance, all right? So let's just find out the variance. Variance of X. So before that, we have to find out the expectation of X square. So what is the expectation of X square? We have to just copy the same thing. And instead of, we have to range over all the values of X. And then instead of this X, we have to just have X square. So 1 square. 0 square, which is just P only, right? So is the variance 0 here? Variance is not 0. don't get do this kind of mistakes. So it is expectation of X whole square, right? So that's why you can just find out P minus P square, which is P into 1 minus P. Okay? P into 1 minus P. So in this case, the expectation variance we have found out. So expectation is P and variance is 1 minus P. P into 1 minus P, right? So this is the variance. This is the expectation. Now I will just ask you to remember this. Okay. See, there are only four popular discrete and random variables, and for those four popular discrete random variables, just remember the PMF. Just remember the expectation and variance formula. We won't drive it again and again. So let me just say that to remember. Okay, or maybe just remember. For Bernoulli random variable, okay? Just remember this about the Bernoulli random variable. First thing, the PMF. How does the PMF look like? X can take value 1 with probability. Is this okay if I just write with WP? With probability P, 0, with probability 1 minus P, right? Here, WP means with probability. Okay. And this is the first thing to remember here. The second thing to remember is expectation of X is P. The third thing to remember is variance of X is P into 1 minus P. Okay. Just remember these things. Sir, for X equal to 0, 1, Bernoulli random variable is defined. Yeah, that's what I'm saying. Only Bernoulli random variable means X is either 0 or 1. Okay. You can call it indicator random variable also. Cool. So just remember this. Actually, we won't be driving, although the derivation might seem easy, but we won't be driving it again and again. Is this okay to everyone? So just remember the slide that if I talk about the Bernoulli random variable, then PMF at least you should remember that what is the PMF of Bernoulli random variable. Okay. So I hope that's fine. Cool. Now, I mean, there is nothing else in the Bernoulli random variable. So that's why let's just move to the next random variable, which is binomial random variable, which is more popular because it is, I mean, in general, like Bernoulli random variable happens. This binomial random variable is actually the repeated trials of the Bernoulli random variable. And it happens very often. So that's why it is again popular. So this is repeated independent trials of Bernoulli random variable, which means, let's suppose you say that you conduct n trials. Okay. So basically, let's suppose you conduct n trials of the same experiment, which means you are tossing n times, right? You're tossing n times. So let me go to the next page. Let's suppose you are tossing not just one time. So earlier we have just tossed one time. Now this time we will be tossing n times, right? You're tossing n times. Now suppose that I say number of heads are k. So what will the number of tails? Will be n minus k, right? Okay. See, this is one template. I mean, sorry, not the template. This is the example of the template, the tossing n times. So basically, in general, what will I say? In general, I will say it is performing experiment n times, right? I will say performing experiment n times, right? And instead of saying number of heads, I will say number of success. I got, if I do something n times, the number of success I got is k. Number of failures I got n minus k, right? Now it is not necessary to say that heads is only success. Tails could also be success. You can definitely write tails here. It doesn't matter. It is up to you how you're defining your success, right? It is up to you. It doesn't matter how you're defining your success. So I hope that is okay to everyone. That which means that this tossing a coin is just a specific example. It is not like that. Okay, for this particular experiment only our Bernoulli random variable is defined, right? It's not like that. Cool. Okay. And now, if I just ask you the PMF of the Bernoulli random variable, which means if I just ask you what is the probability that, okay, X is, let's suppose, number of heads. X is a random variable which is defined to be number of heads. What is the probability that X is 3? Okay. So suppose that if I just ask you what is the probability of X is 3, if we perform, let me just give you the question here itself. The question is saying, we do toss 5 times. Okay. If X is a random variable, which is defined like this, that X is basically number of heads occurred, right? And if I just ask you what is the probability of X being 3, this is the question to be asked. Now, for this question, again, we don't need to know that whether X is a binomial random variable or not. We don't need to know it. We can solve this question without even knowing it. This is one of the very tricky or very nice questions. Just try it out. Just let me know what is the answer you are getting. Anyone? Okay. So, okay, let's just see how to solve this question. Let's just see this, right? Now, what I'm saying that you are tossing 5 times. So what are the possible outcomes? First of all, let me write the solution here. So the possible outcomes could be, I mean, you may have 1, 2, 3, 4, 5 heads. You may have 1, 2, 3, 4, 5 tails also, right? This is 1, 2, 3, 4, 5. You may have tail head, kuch bhi ho sakta hai, right? So there are many possible outcomes. Maybe you can count it using discrete mathematics. How much there are possible outcomes? 2 power 5, right? If you know that discrete mathematics, that is okay. Otherwise, don't worry about it. So basically, there are 2 power 5 items in the sample space. Anyway, don't worry about it. Now I'm just asking that what is the probability that x being 3, which means how many times, what is the probability that x head is coming 3 times? Okay, cool. Now tell me what is the probability of this thing? 1, 2, 3, 1. Tell me this. What is the probability that this particular sequence has occurred? See, what is the probability that this comes and what is the probability that this comes? So basically at the first trial head should come, the 1/2 is the probability. At second trial tail should come, 1/2 is the probability. At third trial head should come. At fourth trial tail, and then at fifth trial head should come. So what is the probability? 1 upon 2 power 5, right? So this is the 1 upon 32 is the probability for this particular sequence. And how many times heads are coming here? 3 times. So what is the answer? That the probability that x is 3, which means 3 times head should be coming. Is this correct? Is this correct? Okay, some people are saying no. Some people are saying yes. Cool. Just tell me if this is correct or not. No, this is wrong. Why this is wrong? Why this is wrong? This is wrong. Why this is wrong? Because this is not the only possibility where heads are coming 3 times, right? I mean, for this particular sequence, yes, I agree that the probability is 1/32, but this is not the only sequence. Do you remember the example I gave you? One, like many times we have done the examples, but do you remember the Hyderabad, Mumbai, one example I gave you, that what is the probability of leading to Mumbai? So basically, like what I'm saying here, if you want to come to some certain conclusion, then you have to add all the probabilities which are leading to that conclusion, right? So you have to sum up all the probabilities that are leading to number of heads to be how much? 3. So basically you have to sum up all the probabilities. Is this okay to everyone? Now this sequence was just one probability. I mean, just one of the case where heads are 3, right? This sequence is just one of the case where heads are 3. But it is not the only case, right? I mean, you can definitely have some case which is something like this. You have to add all the probabilities, isn't it? So if you have to find out that what is the probability that x being 3, it means number of heads being 3, then you have to sum up all of these probabilities. So how many of these particular combinations will lead to x equal to 3? Can anyone tell me? Yes. So basically, if you have 1, 2, 3, 4, 5 positions, then you can select 3 positions out of those five positions, any of the 3 positions, right? So you will say that in 5C3 are the number of sequences that will lead to. So these particular path, this is 1, 2, 3, 4, right? So 5C3 is the number of sequences that will lead to the number of h to be 3. And for just one sequence, what is the probability? 1 upon 32, right? Is this okay to everyone? Okay, you might not be very much comfortable again because you have not seen that permutation and combination and that combinatorics thing. But once you see that combinatorics, then you will be very much comfortable, I think, right? But for now, just try to understand with your little bit of 12th class information that we know about the permutation and combination. But otherwise, you will get to study that in the discrete mathematics again, right? So see here what I'm saying, that here you have 5C3 possibilities. To get number of, I mean, there are 5C3 sequences such that the number of heads are 3. So you have to add all of them, right? So this is, see, the probability of this particular sequence is 1/32. The probability of this particular sequence is 1/32. The probability of this particular sequence, probability of this particular sequence. So you have to, how many of these are there? 5C3, which is, can anyone tell me the answer? 5 into 4/2, I think, right? Which is 10, right? So basically you have 10 possibilities here, which means there are 10 possible ways such that you can lead to number of heads to be 3. So you have to add them, which means 1/32 plus 1/32 plus 1/32. How many times? 10 times, which means 10 into 30, 10 into 1/32. That's what we are doing here, right? That is equal to 10 into 1/32, right? So you have to add all of these. and then you have to get that probability. So don't get confused that why we are multiplying with this. So actually this is one popular confusion, that why we are multiplying with this, why this is not directly equal to 1 by 32. That we have already seen, that why this is not directly equal to 1 by 32, why this is wrong. Are you all convinced that this is wrong? Let me know. Is there anyone here who is not convinced that this is wrong? Do you still think that this is right, that this should be 1 by 32? Okay. AM is saying yes, sir, got it. Satyam is saying convinced. Okay. Okay. So I think everyone is convinced, right? Vishwanath, Gaurav, Abhay. Everyone is convinced that this is 1 by 32. Cool. Akash. Sorry, this is not 1 by 32. Now, which means that it is just one of the sequences leading to 1 by 32. One of the sequences having the probability of 1 by 32. But this is not the only sequence. There are 10 more sequences. I mean, there are nine more sequences, and total there are 10 sequences, which are leading to number of hash to be 3. So I have to add all the probability. That's why we are having this. Right? Cool. I hope that is fine. So that's how we can solve this particular question. Right? So if you ask me what is the probability that x being 3, then what is the answer here? Maybe I can write the answer. It is 1 by 32. Correct? No, right? This is 10 by 32. Because 10 into 1 by 32, basically. You can say 10 into 1 by 32. Yeah, 5c3 into 1 by 32. So now this is correct, which is 10 by 32, which is actually equal to 5 by 16, right? Okay. Take it. Now let's solve this question, which is just the same question, but just a general form of that question. Which means instead of having this this as like earlier I had 1 by 2, I had this as 5, I had this as 3, right? Instead of giving them a general numbers, I mean concrete numbers, let me have the general terms, which means n, p, and k. Let's just work with this question. Can you tell me what is the answer here? Twinkle, can you give me the answer in this particular case? Okay. Okay, I do have answers from most of you guys. So what you guys are saying is, I think, true. Cool. Okay. So the answer is nck into p power k into 1 minus p power n minus k. Great. So let's just see that how to solve this question. What they're saying, what is the probability that x being k, which means they want the number of hash to be k. So out of those n locations, see, these are the n locations that you have to select k locations where you have to have that head, right? And then into the probability of just one sequence, right? So what is the probability of one sequence? You can have, I mean, any sequence, any whatever sequence you want to have, which is basically p power k, because k heads, right, into 1 minus p power n minus k. Okay. So is this okay to everyone? Cool. So that's how you can solve this question. And that is so popular that again you have to remember it. Okay, so I like that is again popular thing. I mean, that is a PMF of Bernoulli random variable, right? Sorry, binomial. Actually, that will happen. I think again. Actually, I just it is just a tongue of slip for me that I just interchange the name Bernoulli binomial. So just remind me, this is binomial. Okay, okay. Let me also do some meditation. Binomial, binomial. Okay, so I hope I'm also, I won't forget that this is binomial. So I might say Bernoulli by mistake, but don't mind it. It is actually binomial, right? So this is a binomial random variable, right? Binomial random variable. So Twinkle is saying, what is the difference? Binomial random variable and Bernoulli random variable. Okay, that Satyam is saying binomial multiple times. So what is the difference? Can anyone tell me what is the difference between binomial and Bernoulli? Okay, this is Bernoulli. The basic difference, binomial. Exactly. So the basic, the core reference, x, the possible values of x here, right? Which means the number of successes. So it is, I mean, here you can say the number of successes. Yeah, you can say, I mean, either it is success or failure basically here, or here it is a number of success, which can be 0, which can be 1, which can be till n. Okay. So the possible values of x, that's the difference. Obviously, and then there will be many differences. The difference in PMF, then there is a difference in everything, right? So obviously the PMF here is, we have just derived the probability of x being k is nck into probability p power k into 1 minus p power n minus k, and here it is PMF of x being 1 is p, right? Okay. Number of trials is 1 in Bernoulli. Yeah, like there is only one trial. Yeah, that is true. Cool. Yes. So yes, that's also nice line, that if you do the repeated trials, okay, repeated trials of Bernoulli is binomial. Is this correct statement, or there is little mistake? Little mistake or correct? Yes, independent is also important. Repeated independent trials. Which means if you're tossing a coin, then our assumption is that if the first is head, then the second could be head or tail. It doesn't matter whatever the first was, right? So repeated independent trials. Okay, then it is binomial. If it is dependent, then interestingly, there is another random variable which is also little popular, but that's not in the GATE syllabus. Okay, repeated dependent trials of Bernoulli is also another random variable. I think if I name it correctly, it is hypergeometric random variable, something like that. Hypogeometric. Actually, I forgot. Hypogeometric or hypergeometric, right? So dependent is also having some popularity, and this is hypergeometric random variable. Yeah. Okay. No, I don't have to flex any knowledge here. I don't think so. Okay. Anyway, so have you understood this? Cool. Now, now this is the PMF of X. Now, what you need to remember. Okay, let's just first derive the expectation and variance, and then we will be remembering. Okay, so find out the expectation and variance for Bernoulli random variable X. So first of all, tell me, if I just give you the PMF, okay, what will the PMF? We have just derived the PMF. If I give you the PMF, do I have to know that this is Bernoulli binomial or something, or for to find out the expectation? No, right? Okay. Can you find out the expectation? That's very and extremely interesting question. Can you find out the expectation here using this PMF? Let me just help you, right? Let me just help you. So let me just help you to find out the expectation of X, where probability like PMF is looking like this. X being K is NCK into P power K into 1 minus P power N minus K. Okay. Which means let me write it in more simpler looking form. I mean the same thing but in the simpler looking form, that if X can be basically 0, can be 1, can be 2, like that, right? So if X is 0, then what is the probability of X being 0? Can anyone tell me what is the probability of X being 0? K is 0, right? NC0 is N. NC0 is N or 1? Choosing nothing. There is only one way, right? So what is the formula of NCR? N factorial upon? Anyone tell me quickly? Is this correct? N minus R factorial. Right. Or not correct? It is R factorial multiplied, right? Or not? Yeah, it is R factorial multiplied. Sorry. Because the permutations are more. Yeah, permutations are more. In case of this combination, you have to divide it. Okay, cool. So now, what is this NC0? NC0, if you just C, it is n factorial upon n factorial, which is 1, right? So this is 1 into p power 0, which is 1. It is 1 minus p power n, right? 1 minus p power n. Okay. Can you tell me what is the probability of x being 1? This is nc1, which is I think n, right? N into p into 1 minus p power n minus 1. Cool. What is this probability? Maybe nc2 into p square into 1 minus p power n minus 2, like that, right? So you can write down all the probabilities. Now, if you want to find out the expectation, then what you have to do? Can anyone tell me? Do you remember how to find out the expectation? Once we have this table, then we just multiply the row wise, right? Row wise multiplication. Okay. Yeah, multiply and add. Yeah, nice one. So we have to find out the expectation. So which means we have to multiply these two, we have to multiply these two, we have to multiply these two, and we have to add all of them. So what is the expectation of x? Maybe you can say this is summation over nck p power k into 1 minus p power n minus k. I mean, this is the term, and k can go from 0 to n, right? I mean, we are okay, and we have to multiply by the k. So this is the probability actually. So this is the probability. So basically, the formula of expectation is summation over all the possible values of k that my random variable can take, and x being k. Now this x being k is this, or maybe you can understand that we need to multiply and then solve it. Okay, is this okay to everyone? Now to find out the expectation, we have to solve this series. Is it looking scary? Right? How many of you think that this is not scary? How many of you think that? Okay, so all of you agree that this is scary, right? There is a good news here. Good news is that, I mean, I will be solving it, don't worry. And that is scary, I also admit it. And then we will be spending 5 or 10 minutes probably just to solve it. But the good news is that we can skip all of this calculation. So let's just do that thing first, which means I will be coming to this little later. Let me just tell you that how you can find out the expectation even without going all of this hectic process. Okay, so let me just call it method 1. This is the method 1 to find out the expectation. But in our life, we will never use this method 1. There is very nice method that I'm going to tell you, and that is method 2, and we will always use the method 2. Okay, so let me tell you the method 2. So let me just tell you that what we are going to do. See, what was the question? The question is that given a PMF, you have to find out the expectation and variance, right? Now, basically, there are two methods to find out the expectation and variance. One is that you directly use the formula, which means you directly plug in this probability value, you directly use the formula, and you find out the expectation. Now, if you find out the expectation, then I like you all are saying that this is scary, and I also agree that this is also scary. So I will come to this. I can solve like we can solve this particular series. Don't worry. But let's just see a method 2, which is actually very easy. Okay. So let's just see this method 2 to find out the expectation. So let's say that x is number of heads or number of success or whatever, right? So let's just say that x is number of heads. Number of heads in a trial. Okay. And what is the trial? Trial is basically, or I mean, what is a trial or experiment? Whatever you want to say. So basically, the trial is there are n trials, right? There are n trials, number of heads, just say number of heads, and the experiment is n times tossing a coin. Okay. And what we want to find out? We want to find out the expectation of x. Let me tell you very simple thing to find out the expectation of x, which means we want to find out the expected number of heads. Is this okay? In English, I can say we want to find out the expected number of heads, right? Okay. So tell me, what are the possible values of this x? What are the possible values of x? Range of x. Can anyone tell me what is the range of x? It can be 0. There can be 0 heads. There can be just one head. There can be 2 heads. Similarly, there can be n heads, right? 0 to n or n plus 1. Tell me, 0 to n or 0 to n plus 1? N only, right? I mean, how can there will be n plus 1 heads? That's very, very obvious. Should it be 1 to n or 0 to n? That's also my question. 0 to n, right? There can be 0 heads also. Cool. So let's just do one thing. Let's define. Okay. So how many trials we are doing? We are doing n trials. Now just listen here very, very carefully. It is actually very important to understand. So just see here. Now we are doing n trials. Let's define. Actually, this method we will be using again and again, and specifically in data structures. In data structures, have you heard about hashing? There is one topic called hashing, right? There in the hashing, we will be seeing the probability of hashing and probability. And I mean, there are complicated formulas in the hashing for the related to probability. So we will be using this method here, there also, right? So let's define a random variable, a separate random variable, basically a separate random variable for each trial. Just listen here what I'm saying here, which means let's suppose that x1 is a random variable for first trial, x2 is a random variable for second trial, x3 is a random variable for third trial. Similarly, xn is the random variable for nth trial. Now I say that these are indicator or Bernoulli or let me just say indicator. Okay, these are the indicator random variables which can take the values 1 and 0s. Okay, it will be taking 1. It will be taking 1 if on the first trial you get head. X1 will be taking 1 if on the first trial you get head. X2 will be taking 1 if on the second trial you get head. So basically X1 is only limited to the first trial. X1 is only limited to the first trial. X2 is only limited to the second trial. That's what we are saying. That let's define a separate random variable for each trial. So if I just say that head, tail, head, this is my outcome. Now tell me what is the value of X2? Looking at this outcome. X2 is 0. Why? Because on the second trial, I got tail. And that's how my X2 is defined. What is the value of X4? It is 1. Because on the fourth trial, I got head. So I hope that is clear to everyone that what is how I'm defining my random variables. So basically, this Bernoulli random variable is actually the n independent binomial random variables, right? I hope my names are correct. Yeah. So nahi yaar, ulta ho gaya. This binomial random variables are basically n independent Bernoulli trials, right? Everyone agree? So basically what we are doing, we are breaking down my binomial random variables into n independent Bernoulli random variables. Yes, sahi hai. Okay, so I think the names are correct. So we are breaking down our binomial random variables into n independent Bernoulli random variables, right? So what we are doing, we are saying that for every trial, let's define a random variable x1. And x1 is 1. Just listen here carefully that x1 is limited to only the first trial. Okay, x2 is limited to only the second trial. X3 is limited to only the third trial. So now, if x1 is 1, x2 is 1, and x3 is 1, let's suppose there are only 4 trials. If x1 is 1, x2 is 0, okay, x3 is 1, and x4 is also 1, then can you tell me number of heads here? Number of heads in total trials are 3, right? Number of heads are 3. So basically, I can say if x1, as I'm saying that x1 is 1 only if the first trial is getting head, x2 is 1 if only if the second trial is getting head. So can I say that, just listen, it is extremely interesting line which I'm going to write. Can I say that x equal to x1 plus x2 plus x3 till xn? Let's understand this using English. What is x in English? Do you remember what is x? Number of heads, isn't it? Number of heads. So let's understand using the semantic meaning. X is number of heads. Now, just tell me using English only. If you add all of them, won't you will be getting number of heads? right? See, if x1 is 1, only if the first trial is getting head. So x1 is counting number of heads in the first trial, right? It is a number of heads in the first trial only. Heads and this is number of heads in the second trial. This is number of heads in the nth trial, right? So if I just ask you, what are the total number of heads in the first trial also, in the second trial also, in the third trial also, you will just add all of them, isn't it? Just add all of them. And these are the number of heads in all the trials. So aren't both same semantically? Right? Cool. That's great. Now finally, what I did, I have just broken down. Okay. We have broken down our binomial random variable into an independent Bernoulli random variables. Right? Which means I am saying x equal to x1 plus x2 till xn. ये एक लाइन के बाद, सॉरी आई एम स्पीकिंग इन हिंदी बट आई थिंक आई एक बार मैं हिंदी में बोलता हूँ, लेट मी जस्ट स्पीक इन हिंदी. ये एक लाइन के बाद गेम इज ओवर. I mean, now you can solve any question of Bernoulli random variable in just a fraction of second. Let me tell you how. Okay, so if you want to find out the expectation of x, then this is same as expectation of x1 plus x2 till xn, which is same as expectation of x1 plus expectation. Just a second, let me use different color. Expectation of x1 plus expectation of x2 plus expectation of xn. And now, can you find out the expectation of x1? Actually, all are identical. So if you just find out any expectation, so this is taking 1 if you get head in the first trial, right? If head in first trial. And what is the probability? The probability is p. So I think that is okay to everyone, right? So the expectation will be p. Is this okay? We have already done this, right? So I think that is okay. So I'm not explaining it in great detail because that should be easy. Okay. So this expectation is p. Now this expectation is p, this expectation is p, this expectation is p, and what is the answer? NP. In just a fraction of second, you can solve the question. Okay. If you know that you can break down this expectation, this x into multiple x's and independent x's. And that is the method that we will be using. And we will not be using this scary method, which means I will tell you how to solve this scary. Actually, this is scary. Let me just tell you. And we will never be using this method. Okay. Which is finding out the expectation directly using the formula. We will not work with the formula. We will not work with this x directly. Okay. In case of Bernoulli random variable, what we will be doing? In case of Bernoulli random variable, we will immediately break down into x1 into x1 to xn. Whatever is the question. Okay, we will immediately break down this x into x1 to xn. That's what we will be doing. In case of Bernoulli random variable, don't work with this x directly. It might mess up. Okay, see, we will be doing some hashing questions. Here in the hashing also, I will say that x is number of items, maybe something like that. Okay, I mean expected number of items I will be asking in the buckets or something. Then also I will be just breaking down this x into multiple parts. Okay, so there will be different type of hashing questions. There I will be actually needing this Bernoulli random variable. Sorry, binomial random variable. And whenever I need this binomial random variable, we will just break down into n independent Bernoulli random variables. Is this okay to everyone? We will just say that this relation hold, that x equal to x1 plus x2 till xn. Okay. So let me know. Like I will come to the method one, but let me know if this particular slide is clear to everyone or not, because this is very crucial to understand that x, which was binomial random variable, is equal to n summation of n independent Bernoulli random variables. Okay, ulta ho gaya. So x was Bernoulli random variable, which is summation of n independent binomial random. Chalo. X, seriously, I'm not pretending it. I don't know what is happening. So x is binomial random variable. which has been broken down into an independent Bernoulli random variable. सत्यम is saying sir रहने दो. हाँ ठीक है, मतलब you got it right. ठीक है, ये Bernoulli random variable है. Okay, cool. This is clear, right? Because this is very important to understand. Once you understand this, then you should be able to solve all the questions. Now you found out the expectation. Now let's just see that how to find out the variance of this, right? So what is the variance? Do you remember variance of the indicator variable? Variance of x, if that is some indicator variable, p into 1 minus p. अभी किया था ना, right? So basically, now you can say the variance of x here is actually equal to the variance of x1 plus x2 till xn. Gaurav is asking then why for all heads? See, head is just one term to understand. Head means success. Okay, they will just say, I mean, we will be solving a question. We will be saying that it is I mean, whatever is a success for you. So x is the number of success. X1 is the number of success in the first try. X2 is the number of success in the second try. Like that. Okay. So maybe with the examples, it will be clear, Gaurav. Okay. It is just a success. It is not about the heads. So x is the total number of success. X1 is the number of success in the first try. X2 is number of success in the second try, like that. So now if you find out the variance, then it will be, can you write like this? If we can write like this, then why? Can anyone tell me? Yes, because of the independency. Do you need that independency in case of expectation? No, right? In case of expectation, you can definitely write without knowing whether independent or not. But here xi's are independent. Okay. And one is, I think, 1 minus p, right? So I mean p into 1 minus p. Everyone is p into 1 minus p. So that's why you can say this is actually equal to n into p into 1 minus p. Some people just say n into p into q. I mean, this q is basically 1 minus p. Okay. I mean, it is up to you. However you like to write. Okay. So that's how you can find out the expectation variance. Isn't the second method very, very easy? It is just a way of interpretation, how you are interpreting this x. Right? Just a way of interpretation. The second method is actually very, very easy. Now, let's just solve this scary looking formula. Okay, just for the sake of completion. Should we do it or should we skip it? Let me tell you honestly, you will never ever need it anywhere in the life, not in the gate, not anywhere, not in your masters or not anywhere. Okay, so let's just skip it, right? Okay, cool. That's actually not needed. So I can solve it, but we will be skipping it. So which means that let me just skip it, but let me just tell you, if you solve it, it will be, what was the answer? N into p, right? But the skip, let me just say skipping derivation, right? Actually, that's not needed. So let's just skip it. Twinkle is saying, sir, writing skip with a heavy heart. No, actually, I'm very happy to skip it because I also don't want to do this. Because see, we will be skipping only if that is not even helping you to develop your skill. Your any intuitive or your any analytical skill. It will not even help you to develop your any analytical skill. It is just limited to this question. See, if something is helping you to even understand anything else, then we will not be skipping. Okay, we know what to skip. I am skipping it because the derivation is only limited to this question and to this particular series calculation, and we don't need it ever. So that's the only reason we are skipping it. Okay, cool. So thank you for saying that skip it. Otherwise, like I was just thinking that okay, I should do it. Cool. So basically, finally, we will be using this kind of method where we will be breaking down this x into multiple xi's and the expectation variances like this, right? Note, we do not need independence assumption for the expected value since it is linear function of random variables, but we need it for the variance. So basically, from here to here, I can say if xi's are independent, then only we need to do it. Okay. Cool. So just remember one thing about the Bernoulli random variables. X is number of success. It can take the range of x is basically, let me write range of x. It can take the value 0, 1, 2 till n. PMF of x, you should be knowing PMF of x, which means x being k is actually equal to nck p power k into 1 minus p power n minus k. Okay. Expectation and variance. Yeah. So just remember these things about the about this. So actually, what we will be doing once the all of this four is finished, all of these 4 discrete random variable will be finished. Then we will be having a table. Okay, we can make a table where I will be writing the possible. This is x. Let's suppose this is Bernoulli. I mean, let's suppose this is whatever Bernoulli. So for Bernoulli, what are the range of x? What is the PMF? I know what is the expectation, like that, right? So we'll be having the 4 rows, and then we can write all of this. So we will be doing it once all of these are finished. So we can make a table. But before that, let me write it separately. So PMF of x is this, and what else is remaining? Expectation of x, right? Expectation of x is n into p. Variance of x is n into pq, npq, right? Npq. Okay. I mean, q here is 1 minus p. Cool. So just remember this. I actually, like, generally you also know that we don't ask you to remember, but if someone is saying Bernoulli random variable, then that is how the PMF is defined, right? So I mean, there is no way you have to remember it, that Bernoulli random variable has, okay, binomial random variable has this PMF. So there is no other way. Like, you have to know this PMF, that binomial random variable has this PMF. Okay. Cool. So let's just solve few questions now. What they're saying, 30 people are invited into a party. Each person accept the invitation independently of others with the probability 1 by 3. Let x be the number of accepted invitations. Compute this following. So basically here, see, either either you understand that you are doing it repeatedly, or you understand that, okay, I mean, there are n things which are n independent things, which means there are n independent persons which can come with 1 by 3 probability to the party, or which they may reject with 2 by 3 probability to the party, and they are doing it independently. So again, here also this x is binomial random variable. Okay. So let's just do one thing. Let's not remember the formula for this particular question. Let's just derive the formula again using x equal to x1 plus x2 plus x3 till xn. Now tell me, for each, see, earlier for each trial we have defined one random variable xi, right? Now for each what we are defining. Yes. Now for every person, very nice, Twinkle. Now for every person, see, there are 30 people, right? So for every people, for everyone, for each person, there is a random variable which is xi, right? Now x1 will be 1. When? Can anyone tell me? When? Yeah, that person is coming to the party. When that person accept the party, right? Coming to the party or accept the invitation, or otherwise it is 0, right? Accept the invitation or reject the invitation. Now they are saying number of accepted invitation. Now tell me, is this equation making sense? See, x is total number of accepted invitations. X1 is if the first person is accepting, right? So basically, commonly it is counting number of persons who are accepting the invitation, right? So this equation by English, it makes sense. Everyone agree? Now, what is the expectation? I think you can find out. So just tell me, what is the expectation here? This question, by the way, I have taken from MIT. So as you know that most of the questions or most of the slides or most of everything we are following with the MIT course. So again, this question is from MIT. Okay. So what is the expectation of x? This is 30 into 1 by 3. This is 10, right? Okay. Actually, there was one question in one of the graph theory test. Okay, in one of the graph theory tests, I actually forgot that question. I will put that question in the quiz. Okay, so I forgot that question. In one of the graph theory tests, there was a question, and the question was something like this. Like, let me just tell you little hint. There was a graph. Okay, there was a graph, and Deepak has given that question, and someone has tagged me in the Gator flow, if I recall correctly. So the graph was something like this. The edge will be present with 1 by 3 probability. something like that. The question was there, edge will be present with 1/3 probability, and then they were asking expected number of edges here. Okay, so basically here for every edge, let's suppose there are NC2 edges, or let's suppose 100 edges or whatever, right? So for every edge, you have to define a random variable x1 on the x. It is either 1 or 0. It is either 1 or 0. Like that, you have to do it. Edge is there or not there. So basically, that was the question in the graph theory test, and we have to apply this Bernoulli binomial random variable concept there. So once you see that question, that will be the question again, either in the weekly quiz, in the graph theory weekly quiz, or in the test series. Okay, so basically, if you are a goclasses student, then you could actually understand the mathematically that why we are doing so. Otherwise, like, people just remember that, okay, this is 30 into 1/3. I mean, they don't have any intuition. They don't have this intuition, which is a very powerful intuition. So if they're asking total number of expected total number of edges, then you define a random variable first of all x. See, they're asking expected number of edges, right? Expected number of edges. The question was something like this, that every edge is present with 1/3 probability. Now they're asking expected number of edges. So whenever they ask you something expected, then what is the first step? You define a random variable without the word expected. So you will say that x is number of edges, right? X is number of edges. Now what they're asking expected number of edges, which means they're asking expectation of x. Okay, and then you have to basically break down this x into multiple x's, and you can solve this question. So basically, this kind of clarity gives you confidence. If you're very clear, then you automatically get the confidence, isn't it? Okay, I have actually removed that slide because I thought that that will automatically be covered. So so here the expectation of x is coming out to be 10, and then expectation of x square. Okay, let's just find out the expectation of x square. How to find the expectation of x square? Anyone? There's a trick to find the expectation of x square. And what is the trick? Without the PMF, you can actually find out the expectation of x square. You just find out the variance. Variance ka to direct formula, you know, right? And using the variance, if you know these two things, these two things, you find out the expectation of x square, right? Okay, so let's just find out the variance. Okay, I'm just showing you the solution. I hope that's fine. So the variance is NPQ, which is 20/3. And if you know the variance, you can find out the expectation of x square, which is coming like this. And then if you have to find out the expectation of this, then since you know the individual expectations, then you can find out this, right? ये binomial है, ये कैसे पता चला? पता करने की जरूरत नहीं है. Like, you don't need to know it. Okay, just go with the question. I mean, you should be just writing something like this. Okay, you should be writing something like this. No, once you have this particular equation, then you know, right? Then you know that this is a binomial random variable. These are the end trials and then expectation. Once you have something like this, then also you don't need to apply the formula. You can immediately derive expectation of x. There's a fraction of second only you can derive. This is NP, right? This is n into the expectation of any of this, right? So the key point here is that you have to just do this. Key point here is that you have to just do this. And once you have this equation, then you should be knowing it, that this is a binomial random variable. Okay, you should be knowing it, that this is a binomial random variable. Cool. So this is the key point, that you're breaking down this x into n independent random variables. Okay. Now let's just do this question. This is again has been taken from MIT. Do you want to give it a try? Okay, just give it a try and let me know. Let me just see that. Suppose that a fair die is rolled 72,000 times. Each roll turns up a uniform uniformly a random number of set this, and the roles are independent of each other. For each set J, let Xj be the number of times that the die comes of J. For each J. Okay, so they have defined X1, X2, X3, X4, X5, S6. Now they are saying X1 is number of times the die come up 1. Okay, number of ones. X1 is number of ones. X2 is number of twos, right? Now they are asking expected value of X3. In the last question, how to find D? Okay, D is easy. See, this is the with the linearity, you can just write it in this form, right? And you already know this, so you can just do this question with the linearity of expectation. Okay, so this X3 is number of threes. Now what they are saying, you are rolling it 7 to 2000 times. Or हर एक की probability is given to be 1/6. I mean, either 1 can come, 2 can come, 3 can come, 5 can come. Now they're saying that what is the expected number of threes? Yeah, just do this question. Okay, so let's just do one thing. Do you want to take a break and solve this question? This is a good question. If you want, you can just take a break and solve this question. Okay, and then in the next video, we can continue. Cool. So let's just meet at 8 p.m. Is this fine to everyone? Okay, cool. So let's just meet at 8 p.m. I will be sharing. Okay, let's just meet at 8:10. Doesn't matter because we have enough time today. Let's just meet at 8 p.m., 8:10 p.m. So I will be sharing a new link. Okay, I will be sharing a new link in the group. Cool. Okay. So thank you, everyone. Just take the screenshot of this question. Just take the screenshot, and if you want to try in between these 40 minutes. Cool. Take care. Bye bye.